but I don't have to teach
We're pretty
you.
much experts.
Yeah, we're experts. I can't explain it to you, but I can
I wouldn't have taught all semester.
What? I should have taught, oh no, yeah, but then like, okay, so you take this scrap and this scrap and you mix it. Now you got this scrap. Right? Yep, you got an A in my test. Yeah, right? Red and blue are opposite, that's all you need to know. You'll be a nurse, you'll be great. They'll retrain you. Right? Remember, let's try. This again. Are we still on this? Last day.
We're on the loop appendage. Okay, so my first point, write that number down, 300 milliosmolar. Yes, those are the units. 300 milliosmolarity. That's pretty much a unit of saltiness. Molarity, you study in chemistry. Osmolarity is biological saltiness because, you know, like osmosis, everything is based on osmosis. But to put in terms of what 300 is, it's pretty much plasma concentration. It's the plasma saltiness, and it's, you know, it's like saline. Saline is basically a 0.9 sodium chloride solution. So that's approximately what is meant by 300, relatively isotonic. I mean, so that's what the concentration of the kidney is in the filtrate when you get to the LOH, the loop of Henle. And what you're doing is the loop of Henle is going to pull water and salt out of the filtrate, and it uses a countercurrent mechanism to pull lots of water and salt from the filtrate. And this will dramatically vary the urine concentration. And in doing so, you can maintain the blood plasma at about 300. So, look at that picture. Look at this one here. This is what we're talking about. Not this one. This one. The longer loop of Henle's of the juxtamedullary nephrons. Now, I still use the term loops of Henle. When you read about it in the books, they may call them nephron loops. So as long as you see the word loop, it's a hairpin loop. It's not really a circle loop, right? And it's the longer ones that can concentrate urine. By pulling water, salt out of filtrate. And the mechanism, the physiology part is called this counter current multiplier mechanism. This mechanism, it multiplies the concentration of the filtrate and the interstitium for that matter from 300 to 1200. I'll drop the units, but as you know, it's milliosmolarity. So 300 to 1200, that's, you multiply it 4 times, and that's what you see on this figure here. Cortex to medulla, 300 to 1200. And let's read what's in the green box. Green box says the long nephron loops of the juxtamedullary nephrons, they create the gradient. Okay, they act as countercurrent multipliers, right? So that's why I want to talk about it. So what I'm writing is, it creates a gradient from around 300 at the top to around 1200 deeper in the medullary pyramid. And so what we're going to see is that you have a multiplier, but then we're going to study the blood supply, which is an exchanger, but both are this word countercurrent, which simply means fluid flows down and then fluid flows up right next to it, okay? Because you have this hairpin loop where, look at this picture here. You have this descending limb of the loop of Henle, and it's thick at first, and then it gets thinner. And it takes a sharp U-turn and kind of goes back up. And it's thin when it starts to ascend, but then it thickens. Okay, so pretend that's one loop of Henle with thick and thin segments, ascending and descending. And the ones we're concerned about is this one. That's the thin descending limb. Filtrate's coming in at a concentration of 300. You just left the PCT. You're going down the loop. Okay? You're coming in at 300. But when you get to the thin descending limb, it's water permeable. So as the figure indicates, water leaves on the way down as you proceed down the thin descending limb. If you lose water from any kind of solution, you're going to concentrate it. Concentrate filtrate. Maybe try to illustrate that to you. That's why it kind of turns brown at the elbow. So maybe it comes in unconcentrated at 300. And as you kind of lose water, as you get to the elbow, they increase the color to, they darken it to like a brownish color to illustrate to you that it's concentrated at the elbow because you lost water. So what I'll write on the board is the concentration of the filtrate at the elbow is 1200. And it's also 1200 in the environment that it's in. That's why they put it 1200 there. So assume on the inside it's also 1200. 1200 milliosmolarity at elbow. Now fluids start to ascend, this concentrated fluid. And when it gets to here, that's the TAL, the thick ascending limb. All right, now look at the slide there. It's watertight. It's impermeable to water. So maybe I'll draw black lines to illustrate that it's watertight. And I'm writing impermeable to H2O. And at the same time, you're not losing water on the way up and out, but you are pumping out salt. And pump means it's an active process, right? So they use red for salt on the way up. So on the way up, you're like not losing water and just pumping out salt. That kind of like dilutes the filtrate back to what it was. What we've done is pulled out water and salt. And that's going to help modify the concentration of the urine. We'll concentrate it. So I'm going to change it from like a brown back to a yellow to finish my color here. So if you were to measure the concentration of the filtrate on the way out, it's probably close to 300. It's probably the same. We're really close to it. Now, so this is, I mean, I illustrated it one time through, but this is continually happening. Fluids never stop flowing. And what you've created is the gradient and a positive feedback loop. And I think the book does a good job of simplifying and just illustrating to you how this countercurrent mechanism, losing water on the way down, losing salt on the way up, is a positive feedback loop. So, I'm going to erase this and do the flow chart there. since it's a loop, I can start anywhere. And I don't like to start where they want to. I like to start where we began, where water leaves the descending limb, because that's kind of the beginning of where it flows down and up. So that's where I'll start. So water leaves. Then descending limb. So we said that. Then, you increase, I'm going to paraphrase this, you increase the saltiness, you increase the concentration of the filtrate. Increase OSM of filtrate. Now add something. We said it was 1200 millismolar at the turn, at the elbow of the LOH. Okay. Now the next thing in the concept map is, well, okay, so you've increased the saltiness at the elbow. Now you've increased the saltiness of the filtrate entering the TAL. Increase OSM of filtrate entering TAL, what I call thick ascending loop. So think of it this way. Now you have salt to pump out. It's easier to pump salt out of a concentrated solution. It's more concentrated. All right, so then you do that. Salt's pumped out. Pump out salt. And as you pump out salt, you're increasing the saltiness of the medullary pyramid. That's the top point. Increase OSM. Let's call it the medullary interstitium, the pyramid. Squeeze it in there. And that feeds back to our first point. Because you've increased the saltiness of the interstitium, more water is going to leave. And if more water leaves, it's going to be salty, and you pump out the salt, and you just keep it going. So as fluid continues to flow, this never washes out. You never wash out, like for example, if water leaves into a salty environment, eventually you'll wash out the salt. But that never happens, because with the countercurrent arrangement, you keep pumping out salt on the way up. So you kind of maintain and keep going. That's why it's a positive feedback loop. You increase the original stimulus, which in this case is water keeps leaving. You keep pumping it out and keep leaving. That's kind of positive feedback part. FB loop. So the end result, by number one, check the box, lose water on the way down. Number two, check the box, pump out salt on the way up, is the multiplier effect. That's kind of the net result. You multiply the saltiness from 300 to 1200. Okay, but that's what happens as a result of this loop, and that's all you need to really understand. And I just focused on two things. This, and then the other one was the TAL. And that really creates, and it's more complicated than that, but essentially, this is what we boil it down to, and I think it's a good simplification. Any questions on this before we talk about the blood supply? There's not too many places in the body where the concentration of the salt is multiplied and it remains that way. Okay, so let's talk about this, the vasorectum. Now understand that I'm teaching the loop of Henle and the vasa recta in different slides, but understand that they're together. Because when we looked at this picture, the vasa recta have gas exchange, and they're associated with the loop appendage. Okay, we're just kind of separating out the picture there. So we're just looking at one thing at a time. So the whole goal of the vasa recta is to understand how blood can be supplied to a salt gradient without, again, washing away the salt. Because blood is always flowing through it. And blood is has a concentration of about 300. So we erase this flow chart. The vasa recta is a countercurrent exchanger. It protects the gradient. It doesn't create it. Vasa recta. It protects that salt gradient. The multiplier created it. This just kind of leaves it alone, so to speak. You're able to supply blood. You get the gas exchange. That's why you go from red to blue. And you just make passive exchanges with the salt. You exchange all the other nutrients that you need. Pick up, the CO2 and metabolic waste products, and you just leave the salt gradient alone. You don't want to wash it away. The kidney loses its ability to concentrate urine without the salt gradient. So all you do, like for example, on the way down, I'll just draw a down arrow. You just make passive exchanges. Blood, plasma is about 300. And as it enters the vasa recta and the blood flows down, it's making passive exchanges. It's equilibrating with this environment. So it's losing water and gaining salt. So I'll just kind of draw, I'll just try to write it out. So basically, in passive exchanges, it does this passively. Capillary beds, these things can flow down their osmotic gradients. Okay. And you're also getting the gas exchange too, but I'm not focusing on that. I'm focusing on the concentration of the blood. Look at the elbow. The concentration of the blood plasma is 1200. We get to the elbow, 1200. And then you go back up. And again, you make passive exchanges. And this is the unusual thing about the vasa recta. Capillaries usually don't make a U-turn, but in this case it does. I mean, if this just left, you'd remove all of that salt. Okay, but you don't. Exit out. You go back up and you make passive exchanges again on the way out. But this time, you're progressively losing salt and gaining water to redilute the blood. Redilute blood. So the net effect of that is, look at the concentration leaving. It's about 325. It's about the same. The point is, you haven't removed that much salt, and you have not disrupted the salt gradient from top to bottom, 300 to 1200. And you're able to supply blood to this area, gas exchange, and leave the salt gradient alone, so the loop of Henle can keep doing its job. And that's usually all we teach in terms of physiology for the loop of Henle. Any questions on the vasa recta or the loop of Henle? Okay, we'll answer this. What's next? What's the next part of the nephron? The DCT. So we're getting close to the end of the nephron. The distal convoluted tubule, the question I always ask is, what's left to be absorbed? Filtrate gets the DCT, you say, well, what's left? Infiltrate. Maybe some sodium, maybe some water. Does the body want it? Do you need to conserve it? If the answer is yes, maybe you're dehydrated, and maybe you need to functionally reabsorb it. And so review aldosterone. Aldosterone, now you've looked at this before, so let's remind ourselves what we learned prior. Aldosterone, it targets the kidney. Now we know it targets the DCT. Well, I'll point to where the figure says that. The distal tubule. Targets DCT, facilitates sodium reabsorption. I believe that's the first question on the test. You target which part of the nephron? What do you reabsorb? Sodium. And what I tried to hammer into your heads on the first test is what follows? Water. Water follows salt reabsorption. That helps increase the blood volume, blood pressure. That's reviewed from test 1. Still got to know it.
What's 2 through 30?
What's that?
2 through 49.
What are you talking about?
I said, what are the other questions? We'll take 2 through
Oh.
39.
I told you the first one. Well, you won't even remember the first one, so what's the point of telling you?
He knows me so well.
Yeah. I frequently tell students what's on the test and you still miss it, because this class is hard. But nice try. Well, look, I got a couple of cups of urine. It's easy to tell which one's dilute, right? So I'm kind of done with the DCT because you already know about aldosterone. But I also want to talk about ADH because they act on the collecting duct. And now we're talking about the formation of concentrated or dilute urine. So I just kind of emphasize ADH. When you get to the collecting duct, the collecting duct, it's collecting filtrate from many nephrons. And it's sensitive to ADH. The principal cell, well, actually, they're called principal cells. There are cells in the collecting duct called principal cells. It's most of the cells. They have aquaporins. The aquaporins, depending on if you mobilize them or not, you can actually form concentrated or dilute urine. Is ADH there or not? So again, here's the figure from before, when we talked about ADH, also known as vasopressin. Can ADH facilitate sodium reabsorption? Look at the figure. That's a yes/no question. And this was a common mistake on the first test, actually. Does ADH facilitate sodium reabsorption? The answer is no. Aldosterone does that, water follows. ADH facilitates water reabsorption, not sodium, okay? But they do kind of work together, the ADH and the aldosterone, to increase the blood volume. But let's look at what you've learned before. Let's remind ourselves. It binds on the cell membrane, you increase the second messenger, you mobilize the aquaporin to insert on the luminal side. The water follows its osmotic gradient, right, from 300 to 600 to 700. Basically, you facilitate water reabsorption by osmosis. But the aquaporin's got to be there. NADH facilitates water reabsorption via aquaporins. Because water just doesn't seep out. Again, there are tight junctions between the cells of the collecting duct, and you have to do a transcellular route. There's a picture side by side showing you the min-max range of urine production by the nephron, focusing on collecting duct. Okay? So this has all been calculated out. So these numbers are real, they're not conceptual. So the formation of dilute urine versus concentrated urine. Let's say you drink a lot of water, you're overhydrated, you're plenty hydrated. Got plenty of fluids. You decrease aquaporins. Great, you decrease aquaporins. What does that mean? More dilute filtrate is passing right through the collecting duct. So if you look at the collecting duct, the filtrate entering is very dilute, about 100. And it's leaving 100. There's no water leaving. And so this is the end result. You can produce about 6 liters of urine a day. And the concentration is about 100. If you're dehydrated, and you want to conserve water for the body, you increase the aquaporins. And you reabsorb most of the water. The end result is you decrease urine output, maybe a half liter a day, and that urine is concentrated, about 1,200. So you increase the concentration, but you decrease the output. Okay, so that's the formation of the concentrated versus the dilute urine. And something that's helping, I put urea on this slide. There's something called urea recycling that reinforces the concentrated urine. I'll put this as a note here. Urea recycling reinforces the salt gradient. Okay, that's why I explain on the PowerPoint slide here. Urea is a metabolic waste product, but it can be used to reinforce the medullary gradient. So urea here, number one, it enters the top of the collecting duct there. In the cortical collecting duct, urea stays in the nephron because it's kind of in a dilute environment. But deep in the medullary region, now highly concentrated, urea will leave, forming a pool of urea that recycles back to the thin ascending limb. So it basically is circulating, it leaves, and it keeps circulating this way. And it keeps pooling here. So now when you get to the bottom of the medullary pyramid, you keep pulling water out. Okay, so that's known as urea recycling. That pool that just kind of is continuously renewed. All right, never drain that out. All right, the collecting duct, those principal cells have the aquaporins, but they also have these intercalated cells for acid-base balance. So we should talk about that a little more time. So most of the cells are the ones with the aquaporins. That's the principal cell. We noted that. Let's talk about the cells stuck in between, intercalated cells. CD, collecting duct. Intercalated cells, or acid-base balance. We got the A's and the B's. So just pay attention to the acid and to the base. It looks like on this one, the way the molecules are arranged, you pump out the hydrogen ions there, and you'll buffer it, okay? And then reabsorb bicarbs there. So let me put a blood vessel in here. So this one, base is going back into the blood, and you're excreting the proton. You have to buffer it, and we're going to talk about those, but that's the idea. Okay, so cell A, when do you want to use those? What must be the imbalance of the pH that you're trying to correct or compensate for? Now you have to think. Let's see. This would raise pH. So this must correct if the imbalance is acidosis. Yeah, that's correct. So that's the imbalance. This compensates. So the opposite imbalance. Alkalosis, pH too high. You just rearrange the furniture. You put the proton pump on the blood side, the basolateral side, and the bicarbonate pump on this side. Oh, I just do the same thing. Shouldn't we draw the opposite? Sorry. So the point is, now you're excreting the base. This will compensate for an alkalosis. The cells just have the molecules on opposite sides. So for example, if I show you any picture like that one, and I ask you that question, what would you say? Could you tell just based on this being filtrate and this being blood? Well, yeah, that should be the type B cell, and you're going to compensate for alkalosis. So now we formed our urine, and now we have to take it down to the bladder for storage. And here's a picture of the male urinary tract. And here's a picture of the female urinary tract, and we're kind of review urethra. We talked about it in repro. So if you look inside the bladder, they've kind of dissected it open there. There's something called the bladder trigone. So think about it. I'm kind of skipping the part where we talked about the anatomy of the kidney. The urine drains out of the first place you have urine, the renal papilla. And what collects it? Minor calyx, and then what? Major calyx, and then what? Renal pelvis, and then what? The ureters descend retroperitoneal. To, as the picture shows, base of the bladder. They don't drain into the top of the bladder, but at the base. And at the base of the bladder, if this is like the bladder wall, and here's the ureter coming in, they do not go in at a 90-degree angle. That will be a 90, but they don't do that, okay? They actually enter at an oblique angle. They don't do this. See if I can draw that. So when they get there, they kind of like, they kind of take a little angle. This is correct. This is what they do. This is, they don't do it. Because you're draining all the urine into the bladder. And what you want to occur is when the bladder fills, the wall of the bladder will stretch, and you want it to shut that orifice. So that way you don't backwash urine back up to the kidney. Okay, so this, check the box, good, because as bladder wall stretches, it closes, we call it the ureteric orifice. So you get to the bladder, and what you see there, the bladder trigone. Well, anyways, at the base of the bladder, you kind of have, I'll exaggerate it. The bladder trigone has two ureteric orifices, which I've drawn as circles there. So we're at the base of the bladder. We have two ureteric orifices. And they kind of drain down to a third orifice created by the internal sphincter. If you cut the bladder open and you look at the thickness of the bladder, thickness of the bladder wall, I should say, the inside of a deflated bladder has rugae, these folds. The bladder wall has muscle called detrusor. I don't want to color it all red, but that's the name of the smooth muscle of the bladder wall. As the detrusor muscle fibers get to the base of the bladder, they form a sphincter called the internal urethral sphincter, and that's the third point of the bladder trigone. At the base of the neck of the bladder there. The internal sphincter. One internal urethral sphincter. It's smooth muscle. It's the same fibers as the trusser, we just call it the internal sphincter. So those are kind of the 3 points of the bladder trigone. If you look at it closely, I mean, it looks like a little water slide at the base of the bladder. And what happens is, as the bladder fills with urine, you start to notice urine in your bladder at about 150 ml. At around 500, your bladder feels full. I think it maxes out at about a liter. Okay, you can Google that, but you got to go at about 500 ml. And I always remember my anatomy professor. He drew a boat and he put like a person in there, illustrating to us that there's a lot of fluid that the bladder holds. And the question becomes, what's going on with these impulses to go? And as the bladder fills, you increase these, what are called afferent volleys to the brain, increasing the urge to go. Increase afferent volleys. So it comes in waves. Basically, quote unquote, gotta go. And so you have this combination of storage reflexes that help you hold it in. But then you have voiding reflexes to help you empty the bladder. And the bladder reflex is what I want to talk about. If you compare male to female, the only difference is the length of the urethra. About 8 inches for a male, a few inches for a female. And the bladder trigone is the same. What I want to map out now are all the nerves that you're responsible for the bladder reflex to either help you hold it in or to help you void the bladder. So let's talk about the afferent division. That's sending information to your CNS, telling you the urge to go. They're pelvic nerves. And so the structure of the neuron is that pseudo-unipolar neuron design, and so we're going to see that in the next figure. So remember pelvic nerves. And for the efferent division, you have, well, there's somatic and autonomic. So efferent, bullet point, somatic, bullet point. There's the pudendal nerve. Now, I didn't draw the external sphincter on my picture on the board, but I could have. There's my urethra. I drew the internal sphincter as just a little sphincter up top. So we're right around there. The external sphincter would just be down a little bit lower. So right around there. Because the pudendal nerve innervates that sphincter. The external urethral sphincter. Now, sphincters are circular muscles, and they kind of pucker when they contract. it'll close off the urethra. So when you stimulate, plus sign, stimulate, that helps you hold it in. You close the tube, you pinch it off. Okay, so that's the pudendal nerve. For the autonomic nervous system, well, there's two divisions. So for autonomic, sympathetic, SYM, there's hypogastric nerves. The sympathetic is actually the nervous system that will help you hold it in by contracting the internal sphincter. I'll put a plus sign, internal urethral sphincter, and you inhibit detrusor. So I'll put a negative sign, detrusor. So if you think about that, nerves that close off a sphincter and inhibit the muscle that empties the bladder, that'll help you hold it in. Okay, so I'll even write, just hold it in, to speak simply about that. Because then the parasympathetic will do the reverse. So the pelvic splanchnic nerves, which are part of the parasympathetic division, pelvic splanchnic. Well, they'll do the reverse. So just underline in red. They'll inhibit the sphincter and they'll contract the detrusor muscle. So they help you void bladder. All right, so here's a figure to study for those reflexes. On the left, hold it in, on the right, void. And so they show you different things. They show you different parts of the central nervous system. So we call this, voiding or urination, micturition. They show you the pons. The pons is kind of where, in the brainstem, these reflexes help you. So you have input from the brain, specifically the pons. And so to hold it in, you feel a full bladder, but you got to hold it in. You got to wait till the lecture's over, then you can go to the bathroom. And the reflex that helps is, well, first, it reaches your awareness, and there's something called the somatic loop, and it's right here. There's a reflex where you just instinctively hold it in. So what they're showing you there is they're drawing. They have the bladder there. And then they draw that blue cell. It's kind of sensory. And then it goes into the central nervous system. I won't draw everything, but when it goes into the central nervous system, that's a reflex, and it's going to synapse to our pudendal nerve. There's our pudendal nerve. That's our pelvic afferent nerves, the blue nerve. So it's called a loop because information is going in, you're synapsing, and then the efferent signal is going out. And you're stimulating the external sphincter. So that helps you hold it in. Now the thing about this somatic loop, I should probably call it that on the figure, on the board at least. It can also receive input from the brain. Well, not from the brain, well, from the pons, okay? Conscious input, because this is skeletal muscle. If you're trying to hold it in, the urge is becoming strong to go, but you just try and try and try just to hold it in a little bit longer, a little bit longer. So I'll draw an input coming from the brain. And I'll just say that, input from the brain. Resisting the urge to go. Really, it's the pons. That's what it says in the top of the video. So that's kind of what you see there. The third thing you see, besides this somatic loop receiving input from two places, receive input from this pelvic nerve, but also input from the brain, the same pudendal nerve. But the other thing you see is the hypogastric. Now the reason why they show you this slice of spinal cord is because the sympathetics come from that region of the spinal cord. So the hypogastric nerve, we have a green nerve there. I'll just draw the postganglionics. I'll put negative sign, negative sign. The hypogastrics inhibit detrusor. And the other thing they do is, if you look, they put a branch, they put a plus sign down there. They're telling you it stimulates the internal sphincter. So I'll just draw another branch going there. So those are the things we already noted. So all of those things, if you, number one, you stimulate the external sphincter, you, number two, you inhibit detrusor, number three, right here, you stimulate the other sphincter. All three of those things will help you hold it in. And the reverse is true if you're going to void. So what they do is, they send a blue line all the way up to the brain, to the pontine micturition center. This is you telling yourself it's time to go. You got a full watt. Okay? You know, if a little bit of urine reaches the proximal urethra, you know, voiding is imminent. You're going to go. So hopefully you're in the right location, right? Voiding is imminent when this synapse occurs. All right, so the parasympathetic efferents, there's three things that they're outlining to you here. So let's kind of go through it. Efferents. Okay, the first thing they show you is you're inhibiting the hypogastric. So there's a branch coming off. You're inhibiting hypogastric. Oh. Remember the hypogastrics, I'll put a negative sign, and I'll also write it out. The first thing I'm drawing on the board is inhibit hypogastric. So in physiology, they say you inhibit the inhibitory, because let's remember what they did. This was inhibiting the detrusor, so you want to inhibit the inhibitory so you can go. All right, so that's the first thing. The second thing is down here. You stimulate the splanchnic nerves so you can contract the detrusor and relax the sphincter. So I'm going to draw another line going down all the way to the sacrospinal nerve. And I'm going to draw one branch going off. Maybe I should draw it a little higher just so we can get the idea here. When I put a plus sign, you're going to stimulate the pelvic splanchnic nerve. Number 2. And at the same time, the pelvic splanchnic nerve, it contracts the detrusor, it inhibits the internal sphincter. So on my notes, I'll put plus next to detrusor. I'll put a negative sign, internal sphincter. Okay, that's what the pelvic splanching does. And the last thing that this parasympathetic efferent does, it inhibits pudendal. Put a negative sign, I'll draw another nerve. You want to inhibit the nerve that contracts the external sphincter. And I'll draw the internal sphincter. I didn't draw it over there. I'll put a negative sign there too. So the last one is third. I'm writing inhibit pudendal. That's this nerve there. And when you do that, you're going to inhibit, negative sign, external sphincter. Okay. So, I mean, check all the boxes. The 2 sphincters inhibit and the 1 muscle contract. That'll help you void. So the only thing hairy about that is try to remember all the nerves to help you hold it in, and students usually have a tough time with that. So I tried to use the same colors as the figure to help you study that. All right, so the last topic for your A&P career, does feel like a career all over the class you take, is using what's called blood sleuthing. And the book I use is your book, the Marriott book. And I teach based on a figure in the book. Let me give you a page number for that, in case you wanted to follow the book after the lecture is over. It should be on 26 somewhere. Yeah, here it is. It's on page 1034 in the Merriam textbook. So let me erase the board. That's a reference page, 1034. Smoothing. Use blood values to determine that, the cause of acidosis or alkalosis in the patient. So the background to understand this, I'll give to you to understand how to solve 8 different scenarios. Of course, there's more than 8 in the real world, but this is most of them. And first thing to keep track of is the respiratory system. In the respiratory system, if it's a cause, if the respiratory system, your lungs, are a cause of either the alkalosis or the acidosis, remember the lungs are responsible for breathing off PCO2. So if it's a respiratory cause, look at the partial pressure, CO2. And the normal range for the partial pressure of CO2 is 35 to 45 millimeters of mercury. Okay, and that should kind of ring a bell. We did have a chapter on that. And that's the normal range. So for example, we know that CO2 can acidify the blood because of our equation. You don't have to write this down again, but I'm just reminding you. Carbonic acid is a weak acid that can partially dissociate and provide a hydrogen ion. That's why it can acidify the blood. So that's why you look at CO2 levels if it's a respiratory cause. So for example, if the pH, just to give you an example, is 7.2, that's low. The normal pH for blood that you should memorize, the normal range, NL is normal, is 735, 745. Okay, and I taught that to you before too. Happens to be a happy coincidence that the 3545 matches 3545. But anyways, that's the normal range. So if you're given a blood value of 7.2, it's a little bit low. And we call that respiratory acidosis. Look at the PCO2 level. What you would expect is that that level should be kind of high, say 46. So if the pH value is low and it's a respiratory cause, that number should be high based on this equation. If you have a lot of CO2, the law of, well, if you have more products, you push it this way to your, if you have more reactants, it drives it to more products. So that will drive the pH down, okay? So that's kind of like the chemistry reason why. Just remember, if it's low pH, high PCO2, that's the general rule, and the reverse is true. Okay, just look at the number. Tell me, is it high or low?
High.
It's high. So if it's a respiratory cause, call it respiratory alkalosis. The PCO2 level, should be low, like say 30. If it's low, you drive it the other way, okay? From this way to the left, So that drives the pH up. So it's kind of like opposite. If the pH is low and it's a respiratory cause, that value should be high, and the reverse is true. So low-high or high-low for the respiratory system. The other system is the kidney, what we just got through talking about, because the kidney is responsible for the excretion or reabsorption of bicarb, if it's a renal mechanism. So let me erase this a little bit. So if it's a renal mechanism, they don't call it a renal mechanism, they call it metabolic alkalosis or acidosis. I'm not sure why, but it's it's the kidney, that's the organ that we're talking about here. And what you want to do is look at bicarb level. Now the units they use in the clinics is milliequivalents per liter. And the normal range should be 22 to 26. And that's the normal range for bicarb. So if it's a metabolic cause, the pH. For example, if the pH is, I'll just give you a number here, 7.30. Is that high or low? That's low. That's low. Remember the normal range? So butyrate lower than 3.5, so that's low. So we call it, if it's a metabolic cause, it's metabolic acidosis. It's probably because the base is low, say 20. The normal range is 22 to 26. So this is low. Okay, that makes sense. If there's low base, low pH. That makes sense to me. And the opposite is true. If it's high, pH high, it's a metabolic metabolic alkalosis. If the pH is too high, you'd expect the base to be too high, say 28. So high, high. And so these are the two systems that you kind of have to merge to kind of solve one of those 8 scenarios. Because we have kidneys and lungs, if one of them is failing, the question you have to ask, is the other one helping? Okay, so that's what we have the whole compensation thing. All right, so first of all, is there any questions on, this is just the background. Well, anyways, look at that top thing I have. ROME. Respiratory opposite, metabolic equal. Now you know what's meant by that. If it's a respiratory cause, respiratory opposite. You expect, oh, well, if that's low and it's a respiratory cause, that's high. Or the reverse, high-low, respiratory opposite. But if it's a metabolic cause, it's equal. Low equals low, high equals high. Okay, that's the acronym. To help you remember that. Okay, now to do the sleuthing, I have to give you values. Let me show you the stepwise procedure to do it. So this does require thinking, So at the end of the last hour, kickstart your last brain cell here, and we'll see if you can solve some of these. There will be a couple of these on your test. And once you figure it out, it's like, oh, I got this. The problem is, can you get to that point? So I'll walk you through a few. I'll give you some to practice. The first thing you should do is memorize, because it will not be given to you, the normal values. Always start with knowing how to identify alkalosis blue, acidosis red. The normal range of pH is the first thing you should know. 735 to 745. The second thing you should consider is the partial pressure of CO2. To 45. That's the second thing. The third thing is the milliequivalence of bicarb. (22 to 26). Then the fourth thing you should do, if you're numbering these things, 1, 2, 3, 4, maybe we should. That's your diagnosis. You can come up with one of these 8 things. And for the purposes of our test, I'll keep it to one of the 8. Every time I give you a problem, there's the answer, one of those 8. And so to figure it out, the blood values I must provide, for example, let me give you some. pH 6.9, 29, 19. So the steps that we should follow based on the book, first just consider the pH value. Is that high or low? That's low. So immediately we know it's some kind of acidosis. Well, what's the cause? It could be either the lungs or the kidney, so then go to step 2. Look at that. Is this number within the normal range? It's low. Now, is that the cause? Low, low. What did we say about respiratory? Yeah, this is not opposite. So all we say at this point is, well, it's outside the normal range, but it's not the cause. Okay. So then go to the third value here, 19. That's low. Low, low. So what we learned was if you have low pH, low base, that's the cause. So it's a metabolic acidosis. So we can write that so far. The last thing you do is say, well, okay, the kidneys are failing, but are the lungs compensating? So what you do is you say, you go back to number 2 and say, evaluate that. Oh, well, let's see, that's low. That's interesting. That's outside the normal range. You know, actually, that would help. By breathing off CO2, you're going to help get rid of acid. Okay? So actually, the lungs are trying to help. So what you say is, with respiratory compensation. So the best way to keep learning this is just to do another one. I'll do a couple more here. So let's go 7.2, 36, 20. So again, I'll walk you through the steps. Step 1, high or low? It's low again. So we already know the patient has acidosis. The next one, is that outside the normal range? No. So it's not a respiratory cause. Move to the next one. That's low. Low, low. We know it's metabolic acidosis. So you kind of circle back. Are the lungs compensating? If they're within the normal range, you say no, they're not compensating. So you just say without the compensation. Without respiratory compensation. Okay, next one. 725, 48, 30. I'll let you do this one with your neighbor. I'll check back in a minute.
Respiratory is high low. Your opposite is renal is equal. So then we know what it's high, low to high. So we know it's a respiratory, and then the pH is low, so it's acidic. So it's
All right, I'm checking back in. The first value, 7.25, that is low. So you notice acidosis. Go to the next value. That's high. So we got the high-low thing. If you have a buildup of CO2 in the blood, that acidifies the blood. That is the cause for respiratory acidosis so far. Then you go to the third value. Are the kidneys compensating? Whenever the other thing is outside the normal range, the answer is yeah. So let's try to make sense of this. Will high base correct low pH? Yes, it will help compensate for that, even though you're still low. So you say with metabolic or renal compensation. Let's do one more. 732, 46, 25. Okay, go ahead, get started, and I'll check back. If you're getting it, you should probably do this in less than 30 seconds. If you're still struggling, we'll still walk you through it.
What did you say about the base?
This
So
one?
why do we look at the base first? Or second, I mean? We look at the pH, then we look at the base. Why?
No, we look at the pH and we look at the CO2.
Oh, I thought you said we do.
Then we look at the base.
Oh, I thought we did it the opposite.
No, we went the same order. 1, 2, 3. All right, what's the cause? It's respiratory what? Again? Acidosis again? Then you look at the base. Is the base helping? What if it's in the normal range? Usually you say no. So there's no renal compensation. So usually at this point, students are totally getting it, or some of you are just kind of behind, or maybe some of you need more practice. So what I want to do is say that I'm going to officially kind of end your last lecture. Yay. 54 hours of lecture, check the box, you did it. Okay. I'm just going to take a couple of tests. But I'll give you more practice problems, and I'll even post some on Canvas just to keep practicing if you think you need it. So at this point, for the rest of class time, just stay and study if you need to. And when's the test? Thursday, what time? 8 o'clock. I'll see you here. Should you leave early? Thanks, guys.
Okay.
Stop.